The focus of this lesson is on evaluating logarithms using four particular properties. And before we go through those properties, I just want you to see from this table that we have the properties listed in terms of base A, base 10, and base E. Either way, the property is the same. If you are dealing with a problem that you're evaluating that has base 10 or base E, you're going to want to write in that base that typically is just understood to be there. And the reason being is from a visual standpoint, it usually helps you evaluate. And so I'm going to go ahead and go through the properties in light of just your general base A. So the first property that we're dealing with is log base A of A is always equivalent to, and I'm just going to leave a blank for the moment, but think about this if you change this to exponential form, and we're trying to figure out this unknown blank here. A, the base A, would have to be raised to what power to get back A? And the answer would be 1. So log base A of A is 1. So that's one way I think about it. The other is, I'll just kind of show it this way as well. This A, we don't see a power on it, but the power is understood to be 1. And then we have a logarithm base A, and then we have this exponential base A. Well, logarithm base A and exponential base A are inverses. So they, in a sense, when you compose them together, undo each other. So if you do log base A and exponential base A, they will undo each other and you'll be left with your x. In this case, my x is 1. So either way, whether you do conversion or you think of that as composing inverses, you should be left with 1. Our second property is log base A of 1 is always, and I'll leave a blank, but again, if you think of this through conversion, your base is A. If you raised it to the unknown power, what would it have to be to get back 1? And the answer is 0. So log base A of 1 will always be 0. So log base anything of 1 will always be 0. If you have log base A of a to the x, then we know that if you do conversion, a to what power gives you a to the x? Well, the power would have to be x. A to the x is a to the x. So that's one way to think about it. Or again, you can think of it through composing inverses. You have log base a, and then you have exponential base a. So log base a of a to the x, think of those as, in a sense, canceling each other out, and you're left with your x. And then fourth, we have a to the log base a of x, and we're trying to determine what that's equivalent to. But what I would have us do on this one's a little more complicated to kind of go through the process of conversion with, but you could, is I'd start off with that log base a of x that's in the exponent, and I might not know what that's equivalent to, but I could say it's equivalent to some y, and then I could convert that form into exponential form, which is a to the y is x, and I know that would be true. But then I can go back to the problem that I was dealing with, which was a to the log base a of x, and I can rewrite it. So I have my base a, and then I'm saying log base a of x is y, and I'm trying to determine what that's equivalent to. Well, we said when we converted that form over here in green that it's x. So it gives me back x. So this is x. Now that's a little kind of confusing to go through that conversion process, but again, this is the exponential base a and this is the logarithm base a, which that means they're inverses. So if you compose those together, they undo each other and you're left with your x. So if I put those properties into motion as far as examples, this is kind of how I go through. So if I have log base a of 8, or sorry, log base 8 of 8, I know that's going to be equivalent to what? 8 to what power gives me 8? The answer is 1. And then if I have log base half of 1, half to what power gives me back 1? I know that to be 0. I see in this third example I have log base 6 of 6 to the 7th. I can see that I'm composing inverses. I have log base 6 and I have exponential base 6. So that's going to leave me my x, or 7 in this case. The fourth example, I have exponential base 3 and log base 3, so those are inverses composed together, will leave me my 5. So that's my x in this case. The same thing, log base 4 of 4 to the negative 2, log base 4, exponential base 4, leaves me my x, which is negative 2. Now, this next example is base e, and that base e is not written in. It's very important that you write it in, because that way, visually, if you cancel out the inverses, you do it the right way. So I have exponential base e, but then I have log base e. So my exponential base e, I cross it out with the log base e, and that leaves me e to the second. For this example here, notice that we have logs within logs. So it's like a composition of logs. Start with the innermost log. So log base 2 of 8. Well, 2 raised to what power gives me 8? And I know that to be 3. So then I would rewrite this as log base 4 of log base 3. And then in parentheses here I had log base 2 of 8. I'd rewrite that as 3 because that's what it's equivalent to. And then I'd start with the innermost log, which is log base 3 of 3. But 3 raised to what power gives me 3? And the answer is 1. So I can rewrite this as log base 4 of, and I'll put the brackets because that's what I had, but log base 3 of 3 we said was 1. So this is log base 4 of 1. Well, 4 raised to what power gives me 1? And the answer is 0. So that's using your properties to get that all the way evaluated down. And then this last example, again, we're dealing with logs and natural logs, so or common log and natural log. I'd write in the base of the common log and write in the base of the natural log. And I can see that I have exponential base 10 and log base 10 composed together, so I'm left with my x. And then I have exponential base e composed with log base e, so that's left with y, and there was a minus sign in between. So it's x minus y when you finish evaluating.